So I hopefully will get through chapter 11. I could spend a whole week on it, but we just don't have the time. So this is a review. And so what I did here, tale of three molecules and the love between them. So we went through turning molecular formula into the molecular shape. Looked at its electronegativity for water. Same thing with sodium chloride. Same thing for CO2. And so what about the love part now? So this is the way they would be situated in the real world. So what you have over here is a strong attraction between two water molecules because of these partial charges, right? Then why does sodium chloride even dissolve in water? It's because there's a strong attraction between the chloride ion and the partial positive of water, and a strong attraction between the sodium ion and the partial negative of water. So this is strong attractions over here. But what about these molecules up here? They're all nonpolar. This is nonpolar because the difference in electronegativity is 0. This is nonpolar because even though it has polar covalent bonds, it's a symmetrical molecule, so all the forces within that molecule cancel out. So these are nonpolar molecules. They're gases, and they're not attracted to anything in here. So they bump into each other and just bounce off like nothing happened. So anyway, I put all that in letters over here. Now I have an interesting question for you to think about. And because I'm going to make you think about it, you're going to understand a lot more than most people will understand. So here's my question. Does CO2 dissolve in water? And it's not a simple question. The answer is no. Matter of fact, I get ahead of myself here. Oxygen, we know, dissolves in water, right? Otherwise fish would die. But why do any of these particles actually dissolve in water at all? They're not attracted to each other. The only way they get in there is if they're going like 1,000 miles per hour. They crash through the surface, they bounce all around, not being particularly attracted to anything, so eventually they bounce off. They're gone. You ask the fish how much oxygen there is in water. Not much. So CO2 does not dissolve in water because it's not particularly attracted to it. But yet, what you're doing right now is you're creating carbon dioxide, which is a nonpolar molecule, in a polar environment called your body. So you're forcing the CO2 to dissolve where it's not supposed to be. So you force a chemical reaction to happen. CO2 will combine with water in a chemical reaction to form carbonic acid. Now, carbonic acid is a polar molecule, so it will dissolve in water. Not only that, you see the hydrogens in the front of the formula? That means that those hydrogens are acidic. So what do acids do? They give off the hydrogen ion and they become anions. So look at this, what's happening here. The more CO2 I put in here, the more I drive the reaction this way, the more of this I make. The more of this I make, the more it drives the reaction this way. And look at these two. These two right here are very soluble in water. So does CO2 dissolve in your body? No. Why does it want to come out of your body as soon as you exhale? Because this entire reaction is reversible. So you exhale CO2 and water. You produce the CO2 within your aqueous body and you force this reaction to happen. CO2 itself is not soluble, but the products of this chemical reaction are soluble. So here's a can of soda right here. You get a sugary, syrupy mix, and then you bubble CO2 into it in as much as you can, then you seal it up. What can you tell me about the form that's actually in the can before you open the can? It's this. And inside the can is a layer of plastic. That layer of plastic protects the aluminum from being eaten up by this acidity. Coke is about, I don't know, pH 2 or something like that. That would eat up holes in the aluminum right away, so they have to put plastic there to protect it. So to answer that question, no, CO2 is not soluble in water. If you force it in, there's a chemical reaction, and those products are soluble in water. But what happens when you open up the can of Coke? It all wants to come out again. Same reason it comes out of your body. You know, I'm not really saying you're like a can of Coke. You're different. Have similarities, though. So here's a summary of the bond angles in the 5 different shapes. So here's linear, okay, 180 degrees. Here's trigonal planar. Here's the shapes over here. And what I put over here is the actual shape. So the theoretical, if everything was exactly the same, would be 120 degrees. But you see that hydrogens are different than the oxygen. So the actual is a little bit less if you look at this angle over here. Similar for nitrite. If you look at nitrate, where all 3 of these oxygens are the same, oh yes, it does become theoretical 120 degrees. If you look at water, it should be 109 degrees, but because the hydrogens are a little bit less repulsive than the electron clouds, it's actually 104.5. So ammonia gets a little bit closer. The ammonium ion, because all 4 of these are the same, it is the theoretical bond angles. So in the higher level ones that don't meet the octet rule, you can see that here's 180 right here, here's 90 right here, and then you have 120 at the equatorial positions. And for octahedral, then you only have 90s and 180s. But you could say, oh, some are axial and some are equatorial. So this is where the names come from. Square bipyramidal and trigonal bipyramidal. So I went through a process myself trying to decide, do I cover expanded octets in this course? For the biochemistry students, you need to know it. For the chemistry 100 students, you don't need to know it, but hey, you saw it, I can't take it back. And I went through the periodic table, look at the oxidation numbers, and I found that there are lots of possibilities for expanded octets. So therefore, it is important to know about them. Now look at these last 2 over here. I don't know if you guys will notice this or not, but look what's the central atom over here. Xena. Sorry, I always say Xena, you know, after respect for the warrior princess named Xena. But anyway, didn't we say that the noble gases don't react with anything? But yet here was showing 2 compounds where a noble gas has to react with fluoride. So, you know what I love about science? Is the constant state of rebellion. Oh, you'll never be able to figure that out. Oh, this never happens. but I don't know for sure, but I would almost guarantee you there was some student in a class taking chemistries, and the teacher said, noble gases can't react with anything. So what did that person do? They went to graduate school, and what was their goal? To make a noble gas react with something. So under normal conditions, this would never happen. But if you put xenon and fluorine gas together and you hit it with bolts of lightning, you might make some of these molecules. So that's scientific rebellion. Especially with astronomy. You see something and you go, wow, what is that? And then you come up with some concept like black holes and stuff. It's just like, okay, that's rebellion in a way. No one's ever thought of it before. But then you have to go out and prove it, don't you? That's what's different between science and other things. You got to prove it. So this is a new concept in chapter 11. I alluded to it a couple times, but it's resonance. So if we look at sulfur dioxide, I am forced to put a double bond between one of the oxygens and sulfur to meet the octet rule for sulfur to make it happy. I could have shared it here, or I could have shared it here. So you see that symbol right there? That double-headed arrow, that's usually what we use to show resonance structures. Without moving the atoms, if you can put the double bond in different places, then you have two different valid Lewis dot structures. And so Linus Pauling used this concept to explain certain things. When they were learning how to break bonds between different atoms, and then finding out how much energy it takes to break those bonds, he found that to break the bond in sulfur dioxide was a little bit harder than in other molecules that had a sulfur and an oxygen. So he used this concept of resonance to try to explain it. So in other words, if you were to direct energy right at this bond right here, those electrons gain kinetic energy. They start bouncing all around the place, maybe out of orbitals. Then eventually you're going to break that bond. But instead of simply breaking that bond, the electrons just resonate over to the other side. So the concept was that electrons, when you're trying to break the bond, absorb that energy by resonating back and forth in the two different forms. So they thought there would be one double bond and one single bond that could resonate back and forth. When X-ray diffraction became precise enough, they could not find a double bond and a single bond. They found only one type of bond in sulfur dioxide. So now the concept had to change. Here's the concept. This is not really a double bond. This is not really a single bond. Both of those bonds are in fact the same. So we say that this bond is 50% double bond character and 50% single bond character. That being 50% double bond character makes it slightly stronger. So does it resonate back and forth? Well, we have no way of looking at what electrons do. So we don't know. But the concept had to change. Now, if you think about Lewis dot structures, this is really nothing more than a human construct. It's an accounting method that they applied to symbols for atoms and valence electrons. So electrons don't have to say, oh, I wonder what the accounting method is going to make us do today. The electrons don't know if they're in a double bond or a single bond or a triple bond or a no bond. Electrons don't know anything, they just exist. So this is a human construct, nothing more. It's valuable because it helps predict things and describe things.
So those are not double bonds and they're not single bonds
That's right.
between sulfur and oxygen?
Yes, that's correct. Mm-hmm.
They are, I'm unclear as to what they are.
Well, first of all, I don't think electrons would like being told where to go by humans.
No.
So electrons just do what they do. So the concept of a double bond versus a single bond is a human construct. That's all.
Okay.
So here's the strategy that most textbooks will do. They'll show you one or two examples, then they'll save a few more for problems at the back of the book, and then they'll save most of them for exam questions. I'm just going to show them all to you. All the common ones, I'm just going to show them all to you. So here's ozone. See? So I could have put the double bond here or here. There's two resonance structures. Similar, selenium dioxide. Here's carbonate. So I could have put the double bond here, here, or here. So again, where am I? Okay. So because I got three places I could have put the double bond, I have three resonance structures. That means that that bond right there is not a double bond. That bond is 1/3 double bond character and 2/3 single bond character. All three of these bonds are identical. So now that you know the Lewis structure for carbonate, you can deduce the Lewis structure for a hydrogen carbonate. This hydrogen cannot go here because oxygen already has two bonds. The hydrogen cannot go here because that would break the trigonal planar configuration there. This carbon can't form 5 bonds. So the only places those hydrogens can go is either here or here. So say I put it here. Now I have this. So I can't put a double bond over here. Now before we have the double bond, carbon has only 6 electrons, right? So it can share from either here or here. It cannot share from here anymore. So there's only 2 resonance structures. So we would say that these 2 bonds are the same. Each one has 50% double bond character, 50% single bond character. Here's sulfur trioxide. 3 resonance structures because the double bond could go in 3 different places. Similar for silicate. Okay. There's a reason why I didn't make you memorize the formula for silicate. You'll learn that maybe later. Nitrite has 2 resonance structures. If you put a hydrogen on it, now you don't have any resonance structures. So this is what you got to be careful with. Say I'm looking at this one right here, and I put a hydrogen on there. I can't put it here because oxygen already has 2 bonds, but I can put it here. And when I do that, notice that that red arrow or line through that means that these are not resonance structures because I had to move an atom to make that happen. So nitrate has 3 resonance structures. Nitric acid has only 2. If you look at dinitrogen tetroxide, if you put the double bond here, okay, you kind of lock in for this one. Then for the other one, you can put the double bond here or here. Then if you lock this one in, then you can put the double bond here or here. So you end up getting 4 different resonance structures, all equal. Here is the acetate polyatomic ion. 2 resonance structures. I could have put the double bond there or there. Here is oxalate, analogous to dinitrogen tetroxide, right? The oxalate ion has 4 resonance structures. Here is nitromethane. So yes, 2 resonance structures. And then we get to this. When you teach chemistry, the stuff you see that makes you angry. So here's what happens if you go online, you start looking stuff up, you look in books, and you start seeing this. This is the predominant form that you see. So from this, you could construe that, oh, okay, I could put one of the double bonds here or there, I could get resonance structures. But in fact, tell me what's wrong with that sulfur right there. 2, 4, 6, 8, 10, 12 electrons around the sulfur atom. Excuse my French, but why the hell is this even on the internet or in textbooks? If we do it the way we're doing it in this class, look at this. There is absolutely no need. There's no need to put double bonds anywhere. There's no need to violate the octet rule for sulfur. So my only explanation as why you see this is that somebody did it one time and they said, hey, that looks cool. We'll do that. And then it just gets in all these textbooks and no one ever thinks about questioning it. So sorry about that. That's just the way it works. So then my concept with the rest of this is to give you an idea of polyatomic ions. So I went through each one, tried to explain a lot of different things. I can't spend a whole lot of time on this because we could spend a whole week on this. But if you have time to read through this, you will learn a lot. So here's where the ammonium ion comes from. It comes from ammonia. So if you look at ammonia, we write the hydrogens on the other side because we're trying to emphasize that that is not an acid. In fact, it's a base. If you look at the way we write water, water has the hydrogens in front, meaning that water can act like an acid. And what do acids do? They give up a hydrogen ion. What do bases do? They accept the hydrogen ion. That's the definition. So we have an acid-base reaction. Now let's think about why this happens. There's that hydrogen. It had 1 electron of its own. It's 1s1. What does it want to do? Get 1 more electron from somewhere else to become 1s2 like a noble gas. So it's sharing this electron from the oxygen. But then it finds out that it's in a problem, relationship. Oxygen is so electronegative that it's pulling both electrons away from it. Not completely, but you see enough to put partial charges, right? So what's the reactive part about water? This hydrogen is not exactly happy. And it's positively charged. What about the ammonia? The predominant feature on this molecule is this non-buying electron pair. So electrons are being pulled towards the nitrogen because it's so electronegative. All that charge kind of builds up on the nitrogen atom. So it's partially negative. Hello, there's the attraction. So if you take ammonia and you put it in water, it's just bouncing around, and who's it bumping into all the time? Water molecules. So every so often, one of these hydrogens says, you know what? You can have my damn electrons. I'm out of here. I'm leaving without my electron. I'm going over here because here's 2 electrons I can call my own. So this non-bonding electron pair becomes a bonding electron pair. And the ammonium ion has 1 proton more than electrons because electrons here in the water were left behind. And in the water, that electron pair that's bonding now becomes non-bonding, but the hydroxide ion has 1 electron more than it does proton, so it has a negative charge. So by the way, if I take ammonia and put it in water, I just made Windex. In addition to Windex, in addition to ammonia, you put a little bit of blue dye so you can see where it's been sprayed, and a little bit of soap. So what happens when this reaction happens, these ions are good at dissolving other things that water itself cannot do. So you wipe off all the grime and everything, then it doesn't leave streaks of molecules because this reaction simply reverses. Water and ammonia just evaporate off the surface of the glass. So, where does ammonia come from? Well, biologically, it comes from eating proteins, which is made up of amino acids. So here's a typical amino acid. Here's the amino part. Here's the acid part. Biochemistry 341, this is the kind of stuff we'll be looking at. So all amino acids have this part and this part. What makes this one different is what's on this carbon right here. This is what makes this amino acid called serine. So all 20 normal amino acids have something different here. All this is the same. So what happens if you metabolize this amino acid? The carbon goes off as CO2. The hydrogen mostly ends up in water, and the nitrogen ends up as ammonia. But ammonia is extremely toxic. I don't know if you want to try this or not, but if you come to your kitchen one night and see a cockroach running around the countertop, what I do is I smash it with something. But what I often do is I take Windex or something like that, and I have it in my hand and I turn the light on. And if I see one, I'm shooting it. Because the ammonia will basically get inside the cockroach's exoskeleton through these little holes called spiracles. What helps it get in there is that a little bit of detergent that's in the Windex. The ammonia goes in there. It's one of the few things that can go into cells. And once it goes into the cells, what does it do? It does this. So it changes the pH of the cell. It kills the cells. If you get enough on there, you're going to kill the cockroach. So ammonia is toxic. Oh, okay. Well, what about us? We eat proteins. If we didn't have the urea cycle, it would be toxic to us as well. So what we do as terrestrial organisms, we take ammonia and CO2, which are waste products, we spend money on it in terms of ATP, and we produce urea, which is another waste product, but it doesn't affect the pH. So urea is what we find that we get rid of our bodies in the form of in urine. It's urea. Way less toxic than ammonia.
Doesn't urine turn into ammonia over time?
It can. This can break down. Yeah, it can. But besides the city and county of Honolulu, this is the only situation where I know where you take a bunch of waste products, spend money on it, and then you end up with a bunch of waste products. So here's a typical molecule, ammonium sulfide. So you can see what I'm trying to do here, I hope. So we just figured out where hydroxide comes from. There's other ways to get it as well. The hydronium ion doesn't exist in a molecule, but this is what happens in pure water. So anybody know the pH of pure water? pH is 7, right? Here's where this comes from. In pure water, all you have is water molecules. But one can act as the acid and the other can act as a base, and you can get some hydroxide and some ammonium ion. So why is water considered neutral? It's not because there's none of this, but it's because the amount of this is equal to the amount of this. So here's a point where I can actually talk about something in Unit 4 called stoichiometry. This is a balanced chemical reaction. One of these has to give me one of these. One of these has to give me one of these. So two of these, every time I make one of these, I also have to make one of these. So these are at equal concentration. Now, when we go to measure the concentration, it's extremely small. 1 times 10 to the minus 7th moles in a liter. That's what M stands for. So 1/10 of a millionth of a mole in a liter. Now, when we take what's called the pH, it's the negative log of that concentration. So the negative log of 10 to the minus 7th is 7. That's where we get pH 7 in neutral water. So the acetate ion comes from acetic acid. Acetic acid is created by bacterial metabolism. So here's acetic acid. You see these 3 hydrogens right here? Those are not acidic because those are in polar covalent bonds. That means that, non-polar covalent bonds. That means that those electrons between the carbon and the hydrogen are shared fairly equally. That means that they're happy. See how we write the formula for acetic acid? Those 3 right there are not acidic. That one in the front is acidic, and that's the one that comes off when you look at the formula for the acetate ion. So let's psychoanalyze it. This hydrogen must be the acidic one. Why? Because its electron is being pulled away by that electronegative oxygen, leaving a large partial positive. In addition, there's another electronegative oxygen over here, pulling electron clouds that way. So that means that carbon wants more electrons, so it pulls that way, which means it pulls this way a little bit more, meaning this is a big partial positive charge. So this acidic hydrogen is not happy. It's still looking for 2 electrons to call its own. So every so often it says, you know what, I'm out of here. I'm leaving. I'm going over here. Here's a water molecule with 2 electrons that I can use. And it leaves its electrons behind. So that's why the acetate ion has 1 electron more than it does protons. And again, the hydronium ion has 1 proton more than it does electrons. It's not a strong acid. That's why this is a 2-directional arrow. If we go this way, then look, these 2 are attracted to each other, aren't they? So it could go backwards and come back and reform this again. So acetic acid is not a very strong acid.
Wouldn't a partial positive be basic?
No, basic, like in pH.
Yeah.
Basic in pH refers to how much hydroxide ion you have.
Okay.
So here's oxalate. So I kind of went the opposite direction. So here's oxalic acid. If I take off a hydrogen using hydroxide as a base, then I get hydrogen oxalate. If I take a second one, then I get oxalate. Okay. So here's carbonate. I did a similar type of thing here. Here I'm taking them off. Here I'm putting hydrogens on, right? So you get the hang of it. Here's sulfite and sulfates. I put them together because they're kind of related. So if you look at the 20 amino acids, 2 of them have sulfur in it. So where do you get fossil fuels from? You take biomass, maybe a dinosaur or 2, but mostly it's plant material, and you bury it under dirt, under high pressure. The temperature goes up from chemical reactions. So you get very hot, high pressure stuff. So all these chemical reactions happen. And after a couple of million years, all those chemical reactions happened. So crude oil, besides burning, is not very reactive. So all those reactions happened already for millions and millions of years. But that means fossil fuel has sulfur in it. So we dig it up, we purify it, then we burn it in presence of oxygen, and we get sulfur dioxide and sulfur trioxide gases coming out. Where else do you get sulfur dioxide and sulfur trioxide gases coming out? Is volcanoes. So if you've ever been to the volcano, what do you smell? Sulfur. So that hot sulfur, elemental sulfur, comes oozing out of the volcano. It's still hot, it reacts with oxygen, and you form sulfur dioxide, sulfur trioxide. Now those, in a similar manner as CO2, combine with water to form acids. So when this washes down in the rain, it becomes acid rain. Most people think, oh, when the new lava field starts to break down, it's because of the plants. No, it's because of the acid rain that comes down from the volcano that helps the plants get a foothold. So then the acids give up their hydrogens to become more stable, become polyatomic ions. So again, I drew all these Lewis structures, shows you how to put the hydrogens on there and the Lewis structures. Then one thing I will tell you, some of the lower level textbooks don't go through sulfite. They only have sulfate. And here's the reason. Sulfite is more reactive than sulfate. Sulfite can turn into sulfate. So here's how that happens. If you take an oxygen atom that came from an oxygen molecule, notice that this has 6 valence electrons. This non-bonding electron pair can become a bonding electron pair, and now you got sulfate. Similar thing with phosphite and phosphate. So here is phosphite. Phosphite can be oxidized into phosphate. I said that correctly. So here is phosphite, hydrogen phosphite, dihydrogen phosphite, and then finally phosphorus acid. You don't have to worry about the acids right now. It's another whole unit. So here's phosphate, hydrogen phosphate, dihydrogen phosphate, and then finally phosphoric acid. Okay. Now I have to go back and tell you another story, because look at this. There's 2 ways to do phosphate. So here's a story about me. You guys ever have professors and like, they just go on and on about themselves? Well, I try not to do that. But I am important, you know? Without me, where would I be? So when I was an undergraduate, I struggled in everything. I was a high school dropout in everything and didn't know it at the time, but very dyslexic as well. So I'm taking chemistry and biochemistry at the same time. And I noticed my chemistry book had phosphate like this. And my biochemistry textbook had phosphate like this. And I'm like, what the hell? Why is it different? So I go to find my chemistry teacher, but he's not to be found. He was way too important to talk to undergraduate students. He teaches class and then run away, so then hide in his lab. I found my biochemistry professor. I asked him, what's the difference? He says, oh, I don't know. I never saw that before. And I'm like, wait a minute, you're the professor. So they didn't know. So finally, I figured it out on my own. If you look at the periodic table, there's the possible oxidation states for phosphorus. Here, we meet the octet rule, 2, 4, 6, 8. That phosphorus is bonded to a more electronegative element 1, 2, 3, 4 times. So it ends up having the +4 charge. If you look at this one, it's bonded to the phosphorus is bonded to electronegative oxygen 5 times. So it's using the +5 charge. But on the other hand, what's wrong with this one? 2, 4, 6, 8, 10 electrons around phosphorus. It's violating the octet rule for no good particular reason. So again, why did they do that? Because somebody wrote it that way, somebody thought it was cool, or they just wrote another book copying the other book. And that's why things like that simply get perpetuated.
When would it be a good reason for like a central atom to have more than 8 electrons?
No good reason.
Never, right?
As we saw in expanded octets, the reason why we make those, they don't find them in nature, but the reason why we make them is because we want things to be reactive so that they actually will do chemical reactions.
Okay, but typically it's always like, it always normally follows the 8 octet rule.
Yep, because that's the most stable, right? So trying to give you some biological applications. Phosphate is symbolized as Pi, or inorganic phosphate. They already knew about phosphate in rocks and minerals. They were so surprised to find the same thing in organic substances, in other words, living substances. And so your cell has a problem. When cells were starting to become alive, they had phosphate in them and they had calcium in them. But there's a problem. If you take calcium and phosphate and put them in the same vicinity, they form a solid that precipitates out of the solution. So to prevent this from happening, the cells had to make a decision. I got to either do something with the calcium or something with the phosphate so they don't come in contact with one another. So a protein was invented called calmodulin. It modulates the concentration of calcium. So calmodulin will bind up calcium and sequester it inside the protein. Okay, so that's how it's handled within the cell. But nature then takes advantage of this insolubility problem to create bone. So here's what bone is. You have osteoblast cells, in other words, bone cells, that produce collagen, which is a protein. They produce it outside of the cells. But that collagen found in bone would be like limp like spaghetti. Okay? So to make it stiff so that we can walk and do things like that, those collagen protein molecules have to be mineralized. So how do they make it mineralized? They use calcium and phosphate and let it precipitate into the structure of collagen. In addition, they keep some hydroxide in there. So altogether, this right here is called calcium hydroxyapatite. And that's more of a common name. Here's the basic structure for the minerals that you find in collagen that finally ends up making bone. So that means that your whole lifetime, you have to keep a certain amount of concentration of calcium, phosphate, and hydroxide ions in the solution. Otherwise, if I take a bone and I simply put it in water, I start to demineralize it. It starts to go into solution. Not very much, but enough to demineralize the bone. That's called osteoporosis when you're a living human. So why do people take calcium supplements? Here's the reason why. Okay. What would happen if you took calcium phosphate supplements? Well, they most likely would never be absorbed because it would just be a solid that would pass right through you. Calcium phosphate might get solubilized in the acidity of your stomach, but then your intestines neutralize that, so it would simply precipitate. You guys love your bones, right? Can you imagine what life would be if you didn't mineralize your bones? You would simply be amoebas, just oozing around the classroom, couldn't get up and walk. You should love your bones. The nitrite can be converted into nitrate, similar to what we saw with sulfite and sulfate and phosphite and phosphate. A nitrite is this, two resonance structures. It basically comes from nitrous acid. The nitrite, you may know, is put into a lot of foods. So here's the problem with nitrites in foods. Nitrate in the form of sodium nitrite is required to be in certain preserved meats, especially hot dogs, luncheon meats, stuff like that. Goes into your stomach, it gets converted into nitrous acid. Nitrous acid will react with amines that are in your stomach because they come from food. And then you end up forming what's called N-nitrosamines. So here's the nitroso group, and it's bonded to this amine right here at the nitrogen. And these are known to be powerful carcinogens. They contribute not much, but mildly to stomach and intestinal cancers. So you may be wondering, okay, if that's the case, why do they still continue to put sodium nitrite into preserved meats? And the reason is that you prevent food poisoning. So I don't know, most people have had food poisoning before. I do come across students who say they've never had it, but I had it before, several times. Remember one time I ate at the cafeteria here on campus. I got sick. I'm trying to go to my car to go home. I couldn't even make it to my car. I'm just laying on the grass, barking my guts out. People walking by, look, oh, a drug addict or something. And I thought I was going to die. And at that time, I had come back from the Army where I got out of shape. And I had gotten back into shape by surfing the North Shore all the time. I could be held underwater for, 20, 30 minutes, no problem. But this thing I thought was going to kill me. So you can imagine if anybody's medically fragile, older, or anything else, food poisoning is going to kill them. So statistically, putting sodium nitrite into foods saves lives. That's why it's there.
That's to prevent bacteria, right?
That's exactly right. Mm-hmm. So here's ways that you can protect yourself from food poisoning, but minimize the amount of nitrite that's in your preserved foods. When my kids were little and the whole neighborhood would come over on a weekend for lunch, they all want hot dogs, right? I would take the hot dogs and slice them up as much as I could, put them into the boiling water, change the boiling water several times. The sodium nitrite is extremely water soluble. You can wash it away. You can actually wash the luncheon meats as well. You lose flavor, but so what? The other thing I would do is cook them. Because if you take nitrite in the presence of oxygen, when you cook it, you will turn it into nitrate. Nitrate cannot form nitrosamines. So here's some structures. Here I put iron 3 nitrate. Okay. And so I found that fertilizers are kind of interesting. Well, you guys like food and stuff, right? Yeah. So here's what happens. Plants that can fix nitrogen have an enzyme called nitrogenase. So they can take elemental nitrogen and reduce it into ammonia and into hydrogen. So, but that ammonia would be a gas. So to prevent it from being a gas, they use some of that hydrogen to turn it into ammonium ion. So then in the process called nitrification, the ammonium ion is converted into nitrite, which is eventually converted into nitrate. Okay? And it's the nitrate that is finally absorbed by plants. That's the source of nitrogen. And one of the major types of high nitrogen fertilizer is ammonium nitrate. So fertilizers are usually, designated by their percent nitrogen, phosphorus, and potassium. Okay. What about cyanide? Well, you probably know that that's the suicide pill, right? And in gas chambers and stuff, you can take sodium cyanide, which is a solid, put some hydrochloric acid on there, and you get hydrocyanic gas form, which is an acid that if you breathe that in, it'll kill you, just like how cyanide does. What cyanide does is it goes through the mitochondria, and it goes to the very, very last step in the electron transport system, and it blocks that enzyme called cytochrome oxidase. And so that's the part where oxygen comes in and gets converted into water. So cyanide prevents you from using oxygen, essentially. You can have oxygen all through your body, but you can't use it. So I came across this guy. This is the golden bamboo lemur. It's an endangered mammal, and in Madagascar, where you find lemurs, the sources of food, sources of nutrition there's not very nutritious. So lemurs are one of the few primates that just get most of their nutrition from eating plant materials. So, other places, there's a lot of fruits and stuff like that. So then there's a competition for what parts of the plant they eat. So most of the lemurs do not eat the new fresh bamboo shoots because the bamboo plant tries to protect itself by putting cyanide in it. So if any lemur were to eat the fresh bamboo shoots, they would die from cyanide poisoning. But the golden bamboo lemur figured out a way to get around it. Before it eats, it goes to the floor and starts eating dirt. In this dirt, there is this clay that absorbs toxins, that prevents the cyanide from being absorbed. It uses iron. So similar to the iron 2 cyanide that I have right here. So this becomes a solid and it can't be absorbed by the intestinal tract. So the downside is to being able to eat cyanide is that you look like this, your eyes are weird, and you're a lemur. And if you're a male especially, it's not a very happy life. Because if they watch lemur behavior, the female lemurs are actually cruel to the male lemurs. They beat them up, they steal their food, they kick them out of their resting place. One of the last times I was going through this, I had a male student in the class, and he kind of like waited for everybody to leave the classroom. And as he walked past me outside the classroom, he goes, "I think I'm married to a lemur." So anyway, this, you're learning so many important things in this class. What if you're suspicious that somebody just tried to poison you? What would you do?
Eat dirt, iron.
Exactly.
Wow. So the iron will bind to the cyanide and save you.
But yeah, potentially. I'm not guaranteeing it. But what do they do to people who are taken to the emergency room with drug overdoses and things like that? What they do is they put charcoal down into the stomach, right? So then the charcoal starts to absorb all the bad drugs, all the toxins, and then they suck the charcoal back out of the patient. And then the charcoal that doesn't come out goes through the intestinal tract, but it still holds on to that drug. Maybe not perfectly, but better than dying, right? So here's some more that we didn't talk about in the chapter 10. All these are in red boxes, right? So you're not required. Here's the superoxide ion right here. Here's the formula for it. So superoxide is formed quite a bit in mitochondria. Okay. Why? Because that's where all the oxygen heads towards in your body. It almost always goes towards your mitochondria. There's not a lot of oxygen there because it's used up quite quickly. But it's also the place where in the electron transport system, you have transfers of an electron from one cytochrome to another, one iron sulfur center to another, one electron at a time. So if an oxygen molecule bumps into that electron as it's being transferred, you'll get superoxide anion. And it's dangerous because it's a radical. That's why you have an enzyme called superoxide dismutase to help you dissipate that. The peroxide ion is another polyatomic ion. It's not a radical. But the peroxide ion would definitely form hydrogen peroxide. And hydrogen peroxide is also formed in your body, and it's extremely dangerous because it can break down in what's called a homolytic cleavage. Normally, electrons either go one way or the other way as a pair. But when they go in opposite directions, in this molecule, you'll get two hydroxyl radicals, which are really dangerous. So all of these is known as reactive oxygen species. And you have a series of enzymes to protect you from this. Superoxide dismutase can do two different things. And then hydrogen peroxide is dissipated by catalase. What about bleaches? Here are the oxychloride ions. Here's hypochlorite. And if you look at Clorox, it's really sodium hypochlorite. So here's what it does. Here's the chlorite ion right here, hypochlorite ion. Here's sodium hypochlorite. Here's something that is going to bleach, is going to oxidize. What does it do? It puts an oxygen on it because that oxidizes whatever X happens to be. That destroys the color of whatever it is you're oxidizing. It may make it more soluble and easier to wash away in the laundry or something. The result is sodium chloride. So what does it do? It puts an oxygen atom onto whatever it's going to react with. That's how it works. So if you look at chlorite, which would you think would be more potent as an oxidizer? Hypochlorite or chlorite?
Chlorite.
Yeah. The more oxygens you have on it, the more it's going to be able to oxidize something, right? So notice you have a series. We have ite and ate. That only takes for 2. So if you don't have enough, or you have less than ite, it's called hypo. If you have more than 8, it's called per. So if you look at the name peroxide, what does that mean? Hydrogen peroxide. Per means oxygen. It has an extra oxygen atom. So as it turns out, bleach, common household bleach, is a very, very dangerous substance. It's super reactive. I don't even know why you're allowed to go to the grocery store, buy a gallon of it, put it on the seat next to your baby, and drive home at 60 miles an hour. And then if you don't have your baby in a car seat, then that's dangerous, but you got your baby right next to a bottle of bleach, that's okay. So you can imagine that perchlorate is extremely powerful. I had some in the lab and I basically gave it up because I probably wasn't going to use it. And every year I got to do all this reports on it and everything. It took like, a couple hours a year to keep track of it. And you should never mix bleach with ammonia. Here's what happens. You get these chloramines, which are gases and extremely toxic. You should never mix bleach with acid because you will produce chlorine gas, which turns into hydrochloric acid in your lungs because of the water in your lungs. And it also produces hypochlorous acid, which is an acid, it's a gas, and it's bleach. So non-chlorine bleach is usually some kind of a peroxide. So what does hydrogen peroxide do? Again, it puts the extra oxygen on whatever it is that it's trying to oxidize. And I'm telling you this because I know how people think. Many of my friends are surfers. Doesn't make them automatically retarded, but yes, they are retarded in many ways. So they think, oh, well, if you put a little bit of something to clean and it cleans good, that means if you put more, it's going to clean better. And if product A cleans good and product B cleans good, you put them together, going to be super clean, brah. Surfers. So I put a bunch of these in there just for you to see. And notice periodate. That's a very strong oxidizing agent, isn't it? So oftentimes in the lab we have potassium periodate, extremely reactive substance. And these I put These three right here are in most lists of polyatomic ions for you to memorize. I took them out because they're simply not biologically important. Can you examine why? They're extremely powerful oxidizing agents. Just like hydrogen peroxide and bleach, I just pour them on the ground outside, they're gone. They're so reactive, you don't find them naturally. So these same way. But the other thing I could point out is this. Notice chromium is a metal, oxygen is a non-metal. There's a covalent bond between them. Why? Because traditionally that's the way they've always done it. Why? Because it seems if you take, say, potassium chromate and put it in solution, the chromium floats around in solution with 4 other oxygen atoms. So they seem to be bound as a group. Same thing here and same thing over here. So this is not what we're covering for other reasons, but if you never see this, covalent bond between a metal and a non-metal, you're going to be totally confused if you've never seen it before. So here is azide. So sodium azide especially is used as a general biocide because it acts just like cyanide does. Not quite as toxic, but it works at the same place. Thiosulfate is interesting because look, it's not symmetrical. Like, what? How could that form? Again, it's not going to form naturally. But here's how you make it. You start off with sulfate, and instead of adding an oxygen from group 6, you add the sulfur from group 6. That's how you make it. And then here's some that are considered minerals. So here's metavanadate. Here's orthovanadate, arsenate, selenate, and silicate. Remember, I did not make you memorize this. You're going to understand why. But vanadate, for example, orthovanadate, for example, is found in the mineral called tokyoite. So tokyoite is found in Philadelphia. No, it's found in Tokyo. So look at the formula for it. Okay. So here is the orthovanadate right here. Here's hydroxide. You can see that you got some barium, some manganese, some iron, and it's found in Tokyo. So the definition of a mineral is something that has a formula that's very, very complicated, but it's the same formula. You can describe it as a formula. If you take a rock, there's no precise formula for you to describe it. But a mineral does have a complicated, oftentimes, but a describable formula. So here's why I did not bother with silicate, making you memorize it. It's easy to be tempted to do that because all you do is you take out the carbon in group 4 and replace it with the silicon from group 4. So you expect that to happen, and it does. But in the environment, it reacts with water, and there's a chemical reaction that starts off as a hydrate, and then it forms these other substances. So most of the time it looks like this. It doesn't look like this. It looks like this. Okay. If I keep it totally dry, I can keep it like this, but that's not really in the environment on planet Earth, is it? So I think finally, it's the borate ions. Yeah, okay. So here's interest. Well, I say interesting. It's interesting to me. Many years ago, I was in Snyder Hall on the 4th floor, and I was above all the microbiology places. And I had a former student who became a graduate student in microbiology. And he took organic chemistry from me, and so he thought I knew everything. And he would come up to the lab and ask me questions about chemistry because he found that, you know, the microbiologists don't really know the chemistry that well. I said, yeah, they do. So he comes up one day and he asked me, oh, what is the formula for boric acid when it goes into water and it kills cockroaches? And I'm like, I don't know. And he got all mad. He's like, I'm supposed to know everything, right? So we looked it up, and over the years, I continued to look it up. And here's what happens. The reason why I didn't know is because it's this variable. So here is boric acid. Okay, here's the formula for it. So yes, it can give off 3 acidic hydrogens and turn into the borate ion. Okay, but when you get boric acid from the store to be against cockroaches, it's in this form. So it can, in solution, form what's called diborate and triborate. And the most bizarre of them is tetraborate. Like what? A rare cyclic form. And notice over here, it doesn't matter where I put the nitrogen. I mean, the negative charges, you can see it's probably going to go 1 each, okay? But with tetraborate, it's very unusual. So I put the 2 charges on the boron because boron normally has 3 valence electrons, so it forms 3 bonds, right? But it needs to have 8 electrons around it. So when you do that, the formal charge usually goes on the boron atom. So it turns out that tetraborax has a common name called borax. And this was used as a detergent for many, many years before modern detergents came along. So why does it act as a detergent? Most likely it's because that hole right here can take a sodium or potassium ion, pull it off of a carboxylic acid, which would be a precipitate, and then dissolve that carboxylic acid. So a sodium could be sequestered in here or in here. Once you make the sodium soluble, now the counter ion becomes soluble. So then it made me think. When I was a kid, when Hawaii finally started to get TV, we had only 3 TV stations. One of them was a Japanese station, so I would watch, you know, the old black and white samurai movies and stuff like that. I should have used that opportunity to learn to speak Japanese. I didn't. But most of the big production shows were sponsored by 20 Mule Team Borax. I never even knew what it was. All I know is that it had good shows on TV. So here's how it turned out. As people were coming across America, going through the deserts in wagon trains and stuff like that, they would cross vast areas where there was borax there, just sitting there on the ground, not belonging to anybody. And somebody said, wow, look at all that white powdery stuff. If I could only find a reason to sell it, I can just sell it. All I gotta do is take it out of there. Then it became known to be a very good detergent. So now how do you get it out of the desert? If you tried to use horses, the horses would simply die of heat stroke. Mules were much more adapted. If you use 18 mules, you'll start losing mules. If you use 22 mules, then you never lose any. It's a waste of resources. So the ideal was 20 mule teams. And they made a lot of money. Anyway, so here's something related to that. Similar thing probably happened. So people are driving around in boats, you know, sailboats back in the day. And so they're passing by these islands that are just full of bird guano. They stink and there's birds all over the place, right? So the birds are fishing, eating stuff. They go land on the island so they can rest and they just plop right there. And so people are sailing around these islands and somebody said, wow, look at all that shit. It's just there. It doesn't belong to anybody. What if I had a way to get it out? I could sell it and become rich. And so people were doing that. Matter of fact, that island nation of, I can't pronounce it, Nauru or whatever, that's their major commodity is bird guano. And every person that lives there is a freaking millionaire because of it. So then, United States had to get involved. The government passed a law called the Guano Islands Act of 1856 because we had to protect our American bird shit. Okay, so Congress can, never mind, sorry about that. So just a couple more things. Here's an ad that I found in a Real Scientific magazine. So this guy is constantly publishing stuff and I'm like, I started to read the ads like, what the hell is this guy talking about? So obviously there's some issues, but it's just, you know, it's hard to understand what this guy is even saying. So the industry scam caused the Gulf oil spill. There's scams everywhere. Everything is a conspiracy. So this guy, John Ellis, has made this machine that saves the environment, saves wildlife, saves ourselves by increasing water solubility. And for some reason, he's putting in here that blood is 94% water. Okay. So here's what he's saying. Their med water that goes through their machine has a molecular bond angle of 114 degrees. Does it stop disease? Oh, yes. It stops disease. Hydrogen peroxide has a bond angle of 111 disease. Does it stop disease? Oh, yes. I mean, is this where President Trump gets his ideas about drinking hydrogen peroxide or something? I don't know. So ordinary water has a bond angle of 104 degrees. Does it stop disease? No. What about distilled water? Now he's trying to tell me that distilled water has a different bond angle than ordinary water. Tell me, what did we learn about bond angles? You think by taking water and running it through a machine is going to change how these electron clouds repel each other? You're going to change a fundamental particle? Remember, electrons are fundamental particles. You can't break them down into anything. So the guy's psycho, but nevertheless, he pays to put his ads in there. And what he's really trying to do is sell you his bottled water. Watercuresanything.com. So I find this to be much more believable. And I saw this ad, it's like he's dressed up like Elvis, right? It reminds me when Bruno Mars was a kid, you would see him down on the streets on Kalakala Avenue. He's like a little kid dancing around doing an Elvis impersonation. And my wife and I are like, isn't that child abuse? But anyway, sure paid off for him, didn't it? And also, I am trying to revive the Chuck Norris jokes because they're so good. And many of you probably don't even know who Chuck Norris is, but look it up. So going through this chapter, let's look at what's going to be on the test, what's review. This part here was simply review. I wanted to reemphasize the perspective that we can look at structure and electronegativity, find out polar versus nonpolar molecules. Why is that important? We can predict and understand how nature behaves. Review. Okay. This won't be on the test for Chemistry 100 at all. For Biochem, you do have a homework with these on it. I might put one on the test, I probably will. Resonance is a new one, right? So although I allude to it in chapter 10, it's here where we go through it in detail. That's on the test. And then you already had to know the polyatomic ions. You might be asked to draw the Lewis structure for polyatomic ions. I'm simply giving you the Lewis structure for every single polyatomic ion. So if on a homework, you're supposed to write the Lewis structure for the ammonium ion, I fully expect you to go look through this chapter and find it. But make sure, if you're just going to copy it down, that you understand what you're copying. Okay? In going through this, you're getting knowledge, you're getting understanding that it would take a chemistry major several years of experience to get. That's why I think it's important. It gives you perspective and makes you appreciate the polyatomic ions. They're all over the place. And then most of this stuff is just your edumacation. It's for your edification. Okay. So anybody have any questions about chapter 11? Was it a lot of material? Yes, it was. But is it a bunch of stuff you have to memorize? Not really. Let's see. Okay, well, I guess that's really all I can cover for today. So tomorrow we're going to do chapter 12. And if you're in biochemistry, today is the last day that you can do your exam 2. And if you're in Chem 100, your exam 2 will be this coming Monday and Tuesday. Okay. And anybody got questions before I just close this out?
Any word on whether Chem 100 will have a review session, maybe on Friday or?
Yeah, we'll try to work that in. Yeah.
Okay, I'd appreciate that. Thank you.
I'm waiting for other meetings to settle in. Yeah. There's a bunch of other meetings that I have to figure out what to do with. That's kind of my problem. If I didn't care about how the university ran, then I wouldn't go to those. Anyway, Okay, well, you guys have a great day, and we'll do this again tomorrow, okay? Okay,
Thank you,
take
Professor.
care. Aloha.